With these problems, the goal is just to find the value of x. Now, remember when you end up taking a square root, you do get a positive and a negative answer, right? The principal root and then the secondary root. So we're gonna just make sure that we do that. So for number one, we can just take the square root of both sides. Don't forget there's a plus and minus. Get x equals plus or minus. What's the square root of 4? 2. For problem number 2, we have to get x by itself first. So let's divide both sides by 2. This leaves us with x squared equals 9. And then we square root both sides, like so. Don't forget the plus minus. We end up with x equals plus minus 3. So positive 3 and negative 3. All right, with these two, we got to be careful because we have to make sure that we simplify the radical. For number 3 and number 4, the numbers that we have are not perfect squares, right? So we have to deal with that. We've got 32 here. We're going to take the square root of both sides just like we're used to. Don't forget the plus or minus. But now we have to break down 32. Well, what comes out of 32? 16 times 2. Here's a prime number. 8 times 2. 4 times 2. And here's 2 times 2. We've got it all broken down into our primes. Let's look. Remember, this is a square root. So we want to find factor pairs, right? So that we can find perfect squares. So we've got 1, 2, 3, 4, 5 2s. So we want to look for perfect squares. A pair of 2s, well, that's 4. Here's another pair of 2s. That's another perfect square, that's 4. And then this one's stuck by himself, so this guy has to stay inside the radical. So we've got this one stays, and then out here we take the square root of 4. We get 2. We take the square root of 4, and we get 2. So on the outside here, 2 times 2, we get a 4. And then don't forget your plus minus, because that's what we had out here, right? So 4 square root of 2 for number 3. We do the same thing with the other one. We've got x squared equals 24. Well, we take the square root of both sides. But then we have to simplify that 24. We have to say, okay, well, what goes in to 24? Let's break that down into its prime numbers. I always like to start with the 2's. 2 times 12. 2 is a really easy thing to divide by. 2 times 6. 2 times 3. Right, and again, write them out. Here's a perfect square pair. That's 4. So 2 is going to pop out. These are not pairs. There's not another 2 to pair this one with. There's not another 3 to pair this one with. So we end up with these two are stuck on the inside of the radical. Two times 3 is 6. And then this is the only thing that came out. So this is what comes to the outside of the radical, just like before. Then don't forget your plus minus. So 2 radical 6. And that's it for these 4. So why am I having us practice solving x squared equations? Well, today we're going to talk about a concept called the geometric mean, and we're going to actually apply it to some to some triangles here. So basically, the idea today is we're going to have um, right triangles, and we're going to cut them in a certain way. I'm going to learn something very special about that. And in order to understand what we have to do, we have to understand something called the geometric mean. So let's jump into that. Let's first talk about the similar triangle situation that we have here. So we're going to take a right triangle, the big triangle ABC. We're going to drop the altitude down. We're going to make a perpendicular line from C down to the hypotenuse, the opposite side. What ends up happening is we create 3 pairs of similar triangles. Because if you look, like the little baby triangle and the big triangle share angle A, and they share a right angle, right? The medium triangle shares angle B, and they both have a right angle. So by angle, the big triangle is similar to the small triangle, and the big triangle is similar to the medium-sized triangle. Which means, well, if this one's similar to this one and this one's similar to this one, we get this for free by the transitive property, right? If A is similar to B and B is similar to C, then A is similar to C, right? Going back to chapter 2, something like that. So what ends up happening is that all 3 of these triangles end up being similar to each other. The big triangle and the 2 little triangles cut by this extra little line down the middle, which is cool because that's going to give us a whole bunch of stuff that we're going to be able to do in a second. So before we get to that, let's practice identifying these triangle pairs, I guess, right? The big triangle, the small triangle, the medium-sized triangle. How do we name them? How do we say that they're similar to each other? All right. So what similarity statement can you write relating the 3 triangles in the diagram? Well, what might help you is to draw these triangles out separately. The big one, X, Y, Z. Let's write the middle one. So we know that Z lines up with Z on the middle triangle lines up with Z on the big one. So we'll put Z here. We'll make another right triangle like this, just like we had before. Z will be right here. Well, what's the right angle for the medium-sized one? It's W. And then the small angle is Y, or not the small angle, but the other angle, I guess, is Y. And then let's do the baby triangle now. We see that angle X lines up with angle X. So angle X is going to go at the top. The right angle here is W. And the leftover letter that we still need to put down is Y. So what's the similarity statement? Well, let's name all 3 together. So triangle XYZ, or that's floating up there so badly, X, Y, Z is similar to, well, X goes with Y here goes with W, Z goes with Z, Y, W, Z, and then the last one, here we got X going with X, Y going with W, and Z going with Y. All right, so we took this picture and we were able to take the 2 smaller triangles and reorient them so that everything matched up and we were able to do everything very easily. All right. I'm not telling you that this is the only way to do it. If you look at the triangle and you got it from the beginning, awesome. Great. Well done. But if you have trouble with that, here's the way, this is the way I would have to do it, because I'm not going to be able to look at that and go, oh, well, it's just such and such and rattle it all off. I'm one of those people, I'm very visual. I need to draw a picture. It's really important to me that I draw a picture, because otherwise this doesn't work right. So I'm going to give you all a chance to do your own. Same idea. You're going to write a similarity statement putting these three triangles together. So give this a try. Okay, so let's go ahead and talk this through once again. If it helps you, redraw the picture so that you're in a situation where you can be set up for success. I know with the medium triangle here on the right, this angle R is the same as the big one, so I'm gonna just draw them out. Here's angle R. The right angle here is P. On the medium triangle, that's called S. Now what's the other one? Is that letter. And then the last one, again, we've got our small triangle. We see that Q lines up with Q on the big one, so that goes over here. The right angle here is going to be called S, and then the leftover letter is P. So we're going to do the same exact thing, right? Triangle PQR. Well, what's that? What PQR? What's that on this one? Triangle SPR. What's the small one? Triangle SQP. As long as you're consistent across the board, you know that you're going to be fine. All right. So now let's talk about sort of our main focus for today. Why are we taking the time to figure out what these special similarity things is for this? It turns out that there's a bunch of special relationships that happen between all of these different pieces and different lengths of sides, and rather than trying to leave it in terms of a proportion like they do here, which is fine, I guess. I'm providing this to you here because I think some of you might prefer to look at it from this perspective, and that's good. But I do want to talk about what I think is a better way to sort of conceive of what is the geometric mean. So we know about the arithmetic mean. We know what this is. We've done this since we were in probably elementary school, where you add up all the numbers and divide by how many numbers there are, right? And divide by the number of numbers, right? Well, if we want to do the geometric mean is like taking all of these and bringing everything up a level. So instead of plus, we're going to multiply. And instead of dividing, we're going to take the root based on how many numbers there are. So here, we divided by how many numbers there are. Here, we count up how many numbers we're multiplying, and we take that level root. So if we're multiplying 2 numbers, it's a square root. If we're multiplying 3 numbers, it's a cube root. 4 numbers, a fourth root, and so on and so on and so on and so on. So that's what we're talking about when we talk about this sort of stuff. The geometric mean, and if you look here, the way that this is set up, if we were to do our cross products and divide and stuff and do all that, we get x squared equals ab, and then square root, which is what we're dealing with here. Now, I personally would prefer to use this one because it's less steps, right? I'm just jumping straight into the action here. But if you like using the proportion and the cross products and this, please, by all means, use it. No one's going to tell you that you're wrong because you're not wrong. It's just there's a bunch of different ways to do the same thing. And so that's an important thing to understand. It's not that it's wrong, it's that it's a different pathway to the same exact answer. Do you think about it in terms of how the geometric mean is defined as a proportion, or do you think about it in terms of how the geometric mean is defined as a measure of central tendency? That is to say, like with the arithmetic mean. The arithmetic mean, you add up all the numbers, divide by how many there are, you get a number roughly in the middle, right? Here, the same thing. You're multiplying all the numbers and rooting them based on how many there are. You're getting a number roughly in the middle. And so it really does. It boils down to what is the conceptualization of this idea that sits best with you. And I'm not going to tell you one way is better than another because it's not, okay? So just be aware there's multiple ways to think about this. It's always going to be your choice which pathway you prefer. All right, so let's get into this. Let's actually apply this now. Why do we care about the geometric mean? Well, let's practice and let's find out what comes from this. So we want to find the geometric mean of 6 and 15. Well, all we have to do is multiply those numbers and square root them, right? So we have the square root of 6 times 15. Now, some people might prefer to take these numbers, multiply them, and then break it down. But I'm sitting here thinking, well, it's already partially broken down. Why would I want to put it back together only to take it apart again? So I'm sitting here thinking, all right, well, 6 is 2 and 3. 15 is 3 and 5, right? Like I'm not going to tell you, no, you're not allowed to write that as, what is that? 90? Yeah. You're not allowed to, don't, don't do that and then break it down. You can do that, but I'm just telling you, if you notice, I was here already. Yeah. Did I get the same numbers down here? I sure did. So do I need to multiply it together just to break it down again? No, I don't. Can you? I'm not going to stop you. It's your drop of ink. It's your bit of graphite. Whatever you want. It's your arm muscle. The more you want to write down, I'm never going to complain about it. But I'm telling you, look, it's already there. So look, what numbers are in a perfect square? Well, look, we've got a pair of threes, right? And then the square root of that is 3. And look, they're by themselves. They don't have a pair, so they stay inside the radical. So the 2 and the 5 stay inside and make a 10. The 3 comes right out here. And this is our final answer, 3 radical 10. Like that. Okay? All right. It's your turn. Give this a try. Okay. So let's go through this. Same idea. Let's find the geometric mean of 4 and 18. And once again, I'm sitting here thinking, well, I don't want to multiply this. Yeah, that's 72, but who cares? Break it down. Right? 4 is 2 times 2. We're breaking it down into its prime factors. So look at what we have: 2, 2, 2, 3, and 3. We're going to make sure that we identify some pairs. 2 times 2 is 4. This is the perfect square. Square root of it is 2. Again, same thing here. 3 times 3 is 9. The square root of that is 3. And here we've got this lone 2 here that doesn't have a friend. And we're going to leave that lone 2 at home while everybody else goes out and plays. These guys come to the outside because we already took the square root. That square root is gone now. And there's our geometric mean. 6 times radical 2. All right, last idea here. So, again, the question is, why? Why are we taking the time to talk about the geometric mean? Why are we doing this? Where does it all lead to? Right? What are we getting at? What's the final idea here? And so let's talk about it. So it turns out, like I was saying before, with the similar figures we can actually create these proportions. And if we create the proportions that are, useful here, we can actually do stuff with it. Like what? Well, look. With this first one, we see that these two pieces right here, AD and DB, if we take the geometric mean of those, we get CD. And likewise, if we take the big side and the small sides, we can actually get the other two sides over here. And they show sort of what we're talking about. Now, I'm going to be very honest with you. Like I said before, I personally don't find writing the statements like this as helpful. I mean, it's helpful, but it's kind of weird looking. It sort of isn't end result motivated, right? We sort of look at that as like, oh, what am I supposed to do with it? I don't know. So this is another diagram that they give in the book. And I want to talk about sort of where does this lead in terms of this diagram. So we're looking, basically the idea is we're going to know some combination of the information up at the top. These two pieces that the altitude split into and the whole length of the hypotenuse are usually, by and large, the information we start out with. And our goal usually is to find these remaining three pieces, the two legs and the altitude. All right. So let's do that. Let's talk about it in terms of those things. What is A? What is the altitude? The altitude is the geometric mean of these two pieces, S1 and S2. The left leg, L1, what is that? Well, the left leg is the geometric mean of the left side piece and the hypotenuse. Right, and these are multiplied. And then the right side piece and the hypotenuse, when we take the geometric mean of those, we get the right leg. All right. So what we have here, this is just a different way of saying that. And then these two are the different ways of saying those two. Do I care which way you go with these? No. If you prefer writing it as the proportion and solving, please do. If you prefer this more end user directed definition, then you can use that as well. But basically, this is what we're talking about. All right. So what I want to do now is I want to go forward and I want to actually calculate some of these things. All right. So, I don't know about you, but me personally, I would rather see this drawn so that the stuff is like you can like look at the sides and stuff. So I personally would take a moment and redraw this so that it was more to the side. That's just me though. If you don't if you don't need that, you don't have to need that. This is a me thing where I like to see the triangles so that I can tell what's what. You know, that I mean again, that's just sort of me as a person. So I'm thinking here, I usually if I can find the altitude one first, I always like to go for that, but it doesn't matter. Um, so we go through, we know that the altitude is equal to the geometric mean of the two pieces. Well, what are the two pieces? 4 and 12. And look, now we're down to what we did before, right? And this is y. I'll change this to a y so that we know what it is that we're looking for, right? Y is a. So let's break it down. 4 is 2 and 2. 12, 3 times 4. Once again, 4 is 2 times 2. So let's write them out. 2, 2, 2, 2, 3. Well, here's a pair of 2's. Here's another pair of 2's. Square root of 4 is 2. Square root of 4 is 2. And this 3 is all by its lonesome. So the 3, all alone, it stays inside the radical. And then these two 2's, we multiply them to the outside, and we get 2 times 2 is 4. So we get y equals 4 square root of 3. Now let's find x. So here, remember that in order to find the left side, we need to take the geometric mean of the left side up here and the whole thing, right? Well, what's the whole thing? This is 4, this is 12, so the whole thing is 16. Well, let's do that. So, this is our H, this is our S1, then this is our L1. So we know what we're looking for. We'll say x equals square root of 4 times 16. Once again, we can break this down. Let's look 2, 2, 2, 2, 2, 2. That's 6 2's. All of our stuff pairs up. That means that this 4 times 16 was a perfect square, which is great. Notice there's nothing to put into the square root. So am I going to have a square root? No square root here. Just 2 times 2 times 2 is 8. And that's our x value. All right. Go ahead and give this one a try yourself. Same idea. You're going to go ahead and give it a try. All right. Okay. Let's go over this one. So once again, we've got this sort of two different things we want to find. We've got the altitude and then we've got the left side. So, maybe it helps to first label the whole thing up here too. So let's find the altitude first. Well, we can break down the 4. We can't break down this 5, so it's just going to be there. Here's our only perfect square thing, so we're going to end up with 2 radical 5. Remember, the thing that stays by itself stays in the radical. The perfect squares come out. And then now we can do the other one. The left piece times the whole thing underneath that radical. And once again, if you notice, everything pairs up here. Which is great, because that means that there's no square root anymore. 2 times 3 is 6. Yeah.